During my time at university, between classes and homework, I've been developing my own game engine from scratch. Specifically, it's a voxel engine, meaning that the game world is built on a 3D grid of discrete elements called voxels. This approach is used by several games, with Minecraft being the most famous example. I chose voxels for several reasons. First, they make it easy to create worlds that can be intuitively modified. The grid-based structure naturally supports dynamic editing of the environment, whether by the player, procedural algorithms, or even autonomous characters. Second, voxels are well suited for procedural world generation. With the right algorithms, the computer can generate vast landscapes, carve intricate cave networks, and populate terrain with unique structures. My goal is to not only let players build and shape the world, but to extend the same ability to NPCs, creating a world that feels alive and reactive. Building a voxel engine also presents technical challenges that I find interesting, from designing efficient data storage to optimizing rendering performance. By developing my own engine rather than building on an existing one, I retain full control over every system and can fine-tune performance to meet my specific goals. In this video, I'll walk you through the progress I've made building the core world system. We'll cover the world structure, rendering pipeline, threading model, and block modeling. I'll explain how pieces of the world, called chunks, are generated, processed throughout the program, and eventually rendered on the screen. One unique feature of my engine is support for arbitrarily shaped blocks. This means that blocks can take shapes other than just cubes, enabling landscapes that aren't completely blocky while still maintaining the voxel structure. Supporting non-cubic models allows for the creation of more intricate structures in varied terrain. In order to understand where we're headed for this project, we need to get into some of the basics of 3D rendering. For games rendering large scenes like this voxel engines, it's crucial to use hardware acceleration through your computer's GPU, which is the graphics processing unit. The ultimate goal for engines that are trying to create a voxel world like this one is to be able to render those voxels. So let's start by looking at how a GPU actually renders to the screen. The GPU excels at a few simple tasks, with the most important for our purposes being drawing triangles. How is this helpful? Well, using triangles, which are the simplest geometric shape, we can draw virtually anything on the screen. For example, I can create a square using 2 triangles, or transform what looks like a 3D box into just a collection of triangles. In fact, we can do this for any 3D shape we want to display. Since a 3D world is essentially just a very complex 3D shape, with enough triangles, we can render out our entire world. The GPU allows us to create long lists of triangles and assign information to each vertex. We can tell each vertex of a triangle that it corresponds to a specific part of an image called a texture. For instance, if we have an image, we can map its 4 corners to 4 of the vertices of the triangles on our cube. The GPU then interpolates the texture across those triangles, resulting in a texture being drawn on the side of the cube. This is the fundamental concept behind 3D graphics. Textures and other information are mapped onto triangles that are drawn on screen. So for our game, we need to generate long lists of triangles that represent our scene. This collection of triangles making up a 3D model is called a mesh. We need to create multiple meshes to compose our 3D world. So now that we understand our end goal, which is sending meshes to the GPU for rendering, let's discuss how we get there. We need a representation of our game world to build meshes from. Because we want our world to be expansive and procedurally generated, we can't store the entire world in memory at once. It would be far too large. Instead, we can break the world into smaller sections called chunks. In this case, chunks are 64 by 64 by 64 block cubic sections of the world. This allows us to focus on manageable sections rather than attempting to handle an impossibly large, complete world. As we build the engine, the definition of a single block becomes more complex, but initially we can think of blocks as either solid blocks or air blocks. One chunk maintains a 3-dimensional array of these blocks. While the blocks and the chunk data structure can be relatively simple, the structure that holds the chunks themselves needs to be more sophisticated. Chunks are loaded and unloaded as the player moves through the world, so we need a data structure to fill this need, with chunks arranged systematically around the player. I created what I call a crawling matrix. I couldn't find an official name for this concept, but it's similar to a 3D double-ended queue. The structure stores all currently loaded chunks in a 3D grid centered around the player. When the player moves far enough in one direction to cross a chunk boundary, the crawling matrix shifts in that direction, dropping chunks that moved out of the range and creating empty positions where new chunks will be loaded. The unloaded chunks are sent to an unload queue to be processed and have their content saved. In this diagram, you can see that if the player moves right, all chunks apparently shift left, and empty slots are generated for new chunks to be loaded on the right. The implementation doesn't actually require copying that data. It uses some implementation details to become more efficient than it looks. So now that we have an idea of the blocks and the chunks that contain them, now we can look at the rest of the program and see how it takes this data structure of chunks and turns it into some renderable meshes that is then rendered to the screen. To understand this, we need to look at the threading structure of this project. Having multiple threads means our program performs multiple tasks simultaneously. We have 3 types of threads: game threads, rendering threads, and loader threads. Each has its own loop, executing the same code repeatedly. The rendering thread needs to loop very fast. Each iteration draws another frame to the screen. The game thread runs at a specific frequency to give our game consistent updates. The loader thread works in bursts, sometimes busy loading and meshing chunk after chunk, and sometimes idle when the player isn't moving or editing the world. Various communications must happen between these threads. When the master loader thread detects an empty slot in the chunk matrix, it instructs a worker thread to start loading that chunk. When the worker finishes loading, it places the chunk in the matrix and adds the chunk coordinates to a shared queue, notifying the master loader of completion. The master loader also assigns chunks that are to be meshed, once again assigning this work to the worker threads. Once meshing is complete, the worker sends the mesh to the rendering thread through another queue. The rendering thread pulls the mesh and adds it to its own collection of renderable meshes. The rendering thread maintains its own crawling matrix composed of renderable meshes rather than chunk data structures. If a player places or breaks a block, the game thread edits the information in the chunk matrix. Since the chunk was previously meshed, the existing mesh won't reflect the updated state and becomes outdated. The game adds the chunk coordinates to a chunks to be remeshed queue. When the master loader notices items in this queue, it assigns a worker to remake the mesh for that specific chunk. Once again, after it finishes meshing, the worker loader thread sends the completed mesh into a queue shared by the rendering thread. The rendering thread then extracts this new mesh from the queue and overwrites the old, outdated mesh with this new one. After this, the world that can be rendered is up to date. So now we know how some of the process works that takes the chunk data structures and turns them into meshes that can be rendered. But we haven't actually looked at the step where the chunk data structure itself is looked at and turned into a mesh. The simplest version of meshing a chunk considers every block in a chunk to be either solid or air. When a loader thread receives instructions to mesh a chunk, it receives the chunk object and iterates through each block. If it finds a solid block, it creates the triangles needed to represent the blocks. As we saw earlier, a cube can be rendered using triangles. 2 triangles to create a square face, and 6 faces to create a whole cube, meaning 12 triangles in total. When the worker thread finds a solid block, it can create 12 triangles oriented to form a cube and add them to the mesh that's being built. After processing all the blocks in a chunk, it has a complete mesh representing the entire chunk, which it sends to the rendering thread. Here's the first version I implemented early in development. In this example, I'm using 3D Perlin noise to generate some interesting world shapes. However, there's an issue. If we move our camera inside the solid structures, we can see that all the block faces are being rendered, even when they're inside the solid structures. These faces would never be visible to players, so rendering them wastes both memory and decreases performance. We can fix this in the meshing code by skipping the creation of unnecessary faces. In this improved meshing code, we still iterate through every block, but examine each block's neighbors. If we find a solid block with the solid neighbors to its left, we don't need to create the left face for that block, as it will be blocked by its neighbor. In this 2D example here, block A has a block above it and to the right, meaning that only the downwards and leftwards faces of block A actually need to be rendered. We apply this logic to all 6 directions. The result is a hollow-looking interior of chunks, but there's still an issue at chunk borders. Blocks at chunk edges don't know about neighboring chunks, so they can't determine whether to create boundary faces. This is something that can be seen in one of the early iterations of the design. As we move the camera inside of this solid region of blocks, we can see it's mostly hollow inside, except there's a solid wall of faces at the chunk boundary. To solve this, we give the loading threads access to the chunk matrix. When meshing a chunk, the thread can examine neighboring chunks when dealing with boundary blocks. However, if a chunk loads before its neighbors, it still can't access neighboring information. My solution for this is that when a chunk loads, instead of immediately meshing that chunk, we check its neighbors. We only assign a chunk for meshing once it's fully surrounded by neighbors on all 4 sides. This ensures that chunks can be meshed without issues, because all neighboring information is accessible. For example, if we have chunks 1 through 4 loaded as shown here, and chunk 5 gets loaded, it will attempt to mesh all of its neighbors. The only neighbor that's actually in existence is chunk 4. Chunk 4 realizes that it's completely surrounded by loaded chunks, and therefore its mesh is able to be generated. So after chunk 5 is loaded, the mesh that gets generated next is actually for chunk 4. We can see the results of this improved algorithm in the latest version of the game engine. As we fly inside of the map, we can see that no faces are being rendered that the player would not be able to see looking from the surface of the world. So far, we've dealt with simple cubes, but one feature I wanted in this engine is support for arbitrarily shaped voxels. I made a system where voxels can be designed in any 3D modeling software and then converted into a format readable by the game engine. When importing arbitrarily shaped voxel models, we don't want to lose performance benefits of selective face inclusion. For any imported model, we need to track details about each face. If a model has a full face where one side covers a complete square of the voxel's bounding box, that face can hide the voxel it points towards, just like a full block covering another block's face. If a voxel model doesn't have a full face but has geometry against the bounding box side, it might still obscure some voxel types. For example, 2 ramp-shaped half-cubes sitting together don't have full faces on either side, but their faces still obscure their corresponding neighbors. When importing models, we flag any face completely covered by the model. If they're not complete, we trace the shape their edge face creates, as it has the potential to cover other neighboring voxels. To handle this, I created a secondary program that processes .glb files, which is a specific 3D model file format. The model processing program imports the existing 3D model file, reads all vertex and texture coordinate information, then normalizes vertex positions between -0.5 and +0.5, creating a block within the 1x1x1 voxel size appropriate for a game. It then examines each face of the bounding box, determining whether each face takes up the complete square. If so, it flags that face. If a face isn't complete but still has triangles on the face plane, it traces the outline of that external face. A voxel will have a complete face if the face contains 2 triangles that touch all 4 vertices of the face. For partially covered faces, the algorithm works as follows. A point outside the bounding box is chosen arbitrarily, and a line is found to one of the face's vertices that doesn't intersect any other lines. The face contour is then traced, keeping to the outside. The line from the outside point to the starting vertex, which doesn't cross any other face lines, ensures that this vertex is on the face's exterior. A path is then traced, keeping to the face's outside, mapping the complete face pressed up against the bounding box's outer edge. Currently, these face outlines aren't used in my up-to-date version, but they should be implemented going forward. Only the full face flags are currently used for neighbor checking. With this new system, we can now incorporate any arbitrarily shaped voxel into the world. To demonstrate, I created a voxel from the Utah teapot, a famous 3D model used in computer graphics demonstrations quite frequently. Of course, the main use case for custom models will be simpler geometric shapes like ramps, stairs, cylinders, or partial block sections. This system opens up possibilities for much more varied and interesting world generation while maintaining the performance benefits of the voxel-based approach. This brings us to where I am currently with the project. There are a couple of optimizations and details that I didn't dig into in this discussion here, and I might describe some of them in a future video. This includes the ability for voxels to be rotated, the texture and material system, which allows the same block model to have different materials applied to it, vertex packing, where I compress the information attached to each triangle vertex into 12 bytes, where it would usually take up 34 with the standard approach, and biome generation, though my current implementation is still a bit primitive. Stay tuned for a future video where I get into some of the lower level implementation details behind the engine. In the meantime, if you are new to the world of voxel game engines, or even 3D graphics as a whole, I hope you were able to learn something new today. If you find these concepts interesting, I encourage you to dig into them yourself. If there is a specific question you have, or want to discuss something you noticed about my engine, head down to the comments and I will do my best to give you a reply. I look forward to letting you all know how this game engine continues to evolve, but until next time, stay curious.